In section 6.2 and in 6.3, we're going to be looking at what's called volumes of revolutions. These are things where you have some sort of area, you rotate that area around a line, and you get something that has a circular cross section. We're going to look at finding the volumes of these objects. So the first way we're going to do that is by using disks. And let me show you what we're going to do. Let f of x be a function that is positive between a and b. So you've got something like this from a to b. And let's rotate it around the x-axis. So what we're going to do here is take this, rotate it around the x-axis. Let's shade the area in first. That's good enough, mostly between the lines. So if we take that and rotate it around, what we're going to get is over here we'll have a similar sort of thing. But my drawing here is leaving out, it's really just showing the reflection of it on the bottom. Really, there are cross sections here that we would get that are circular. And this can be kind of difficult to visualize, so let me show you a tool that we can use to help with that. This is my website. There's a very old picture of me there. And if you come here, this is the URL for it's wesca.edu//cleach. And if you click here on volumes by disk/washers, it'll take you to this. And you can zoom in on this a bit. And what I've got here is I've got f of x, that's my upper function, is 4 minus x squared. That's the parabola there. And then g of x is 0. So if I click shade area, and notice I've told it to go from 0 to 2. So it shades all that area. If I change this to say 4, then we get that part of it too. But let's keep it at 2. All right, now to rotate this around the x-axis. The x-axis is the line y equals 0. So if I just click rotate, it rotates it around and it shows us this sort of shape that we have that we're going to find the volume of. Now, one thing you'll notice, this shape, it's an approximation, because instead of the, you'll notice it has these little steps on it. Well, what we're doing here is the same as what we did with areas. You know, with areas, we approximated an area under a curve or between two curves by looking at a bunch of rectangles and adding them up. And we had little errors in there as well. Well, the same thing happens here with this. If you take this and let's see, if we look at it from the side, tell you what, I'm going to turn this down to 10. If we do this, we're approximating the area of this solid by just looking at 10 different disks. And we're cutting this into disks from the side. I can adjust the opacity here, so we can do that and then we can see the different disks. So we've got a bunch of disks stacked up on top of each other. And this tool goes ahead and tells you the approximate area. It's 53.6 or 17.06 pi. If I change the number of, let's turn the opacity back up. If I change the number of disks, right now it's at 10. If I change it to 100 and then click rotate again, then it gives us this. So we've got a bunch of disks here. And this is going to be really close to the actual area. I can again turn the opacity down and see these things. So what we want to do here is come up with how do we find the volume. And so what we need to do here is we need to come up with a formula for the area of a disk, and then for the volume of a disk, which we'll get by just multiplying the area by the thickness, which is going to be, in this case, dx, because from one side of the disk to the other is a tiny change in x. And so by doing that, we'll be able to calculate the exact volume of this thing. So let's go back and look at the first example. The first example is take the area, well, it's exactly what we just had in the drawing, or on the animation. Find the area under 4 minus x squared. Before we do that, though, let's work out the just sort of general disks. This is a disk, and let's see, it's the area. Notice if this is f of x is the radius in this case. So what we want for this disk is, let's see, the volume of the, let's start with thickness. The thickness of the disk is a tiny change in x. All right, so its volume is equal to the area of the circle times the thickness. And of course, the area of the circle is pi times, I'm going to write this out, radius squared times thickness. And this is the gist of the disk. So that's the disk volume. The volume of the solid is what we get by integrating this from a to b. Pi radius squared times thickness. And that's what you should memorize. Sometimes they will, sometimes books or study guides, things you find online, will tell you pi times f of x squared times dx. Don't memorize that. That will, that's true for the first simplest case, but when you start rotating around different lines and things, that'll fall apart. So just keep in mind that you're doing pi times radius squared times thickness. And again, this is the cross-sectional area. This is the thickness. So when you multiply those two together, you get volume. And then the integral just says you're adding up the volume over all those places. So let's come down here and look at this example. There was a typo on here. This is supposed to be 4 minus x squared. So if we take this and draw it, here's 4 minus x squared. And the area that we're going to rotate around is this. So if I take that and rotate it around the x-axis, it comes down here. And now I need to draw in one of my disks. So you just pick any place in the middle and you draw your disk in. Like that. And I like to give it a little bit of thickness like this. So that's one disk. And once we've got that, let's start labeling it. This up here, I'm going to pick a point. This is the point x, 0. And x goes from, let's see, from here to here. So it goes from 0 to 2. All right, the point up top, its x-coordinate is x. Its y-coordinate is 4 minus x squared. And so on this thing, I probably should have written this first. The thickness is dx. The radius. Now on this one, the radius is just 4 minus x squared. And we can see that because that's the length of this line here. Sometimes it's not, sometimes you can't just read it off immediately, but the way you get that is by doing this minus this. All right, so that means that the volume, and I'm going to go ahead and just write the volume of the whole thing. It's the integral from 0 to 2 of pi times the radius squared dx. So now it's just a matter of working out this integral. And let's see, we've got plenty of space. Let's do that. I'm gonna slide this over here. So first up, my volume, this integral, let's see, we get pi. I'm going to pull that out front. Okay, if we square that 4 minus x squared, we're going to get 16 minus 8x squared plus x to the 4th dx. And if I integrate, I'm going to get pi out front And then this will be 16x minus 8/3 x cubed plus 1/5 x to the 5th. And we're supposed to do that from 0 to 2. All right, so if we've got the pi out front, this first bit is going to be 16 times 2 is 32, minus 8/3 of 8. Let's see, 2 to the third is 8 times 8 is 64 over 3, plus 1/5 of x to the, 1/5 of 2 to the 5th. So that's 32 over 5. And of course, we don't have to plug the 0 in because it would make all those terms 0. All right, we're big kids. We could do fractions if we wanted to, but I'm just going to stick it in my calculator. 32 minus 64 over 3 plus 32 over 5. When I do that, I get 256 over 15. So the exact answer is 256 pi over 15. So my calculator is showing me that. If I hit the button, let's see, where is it? If I hit the button, it gives me an approximation. The approximation is 56.6165. And that's our volume. Let's compare that to what the computer found. If we go back over here, yeah, 56.6165. Now, one thing, I wrote this page in JavaScript and 3JS. The way that this page actually computes that volume is not by, it's not using the same method we just used. It's actually doing it numerically by finding the volumes of all 100 of these, disks and adding them up. Every one of those disks would have a width of 2 divided by 100. So what, 50th? But anyway, that's what the window does. I'm gonna go back to this a good bit. I really need to clean up this web page. There's some stuff here at the bottom, these window settings. Pay no attention to those; they don't work. But anyway, that's how you use the disk method to find an area. I want to do some more examples, but the video is getting long, so let's save the other examples for the next video.